Today we're going to talk about graphing linear inequalities in two variables. Earlier this year we did it with one variables with the number line. Remember we had the open circle and then the bold arrow going to the left or the right based on the inequality of less than or greater than. Or we had the closed circle, and we want to remember what those kind of looked like as we build this one. So the linear inequality in two variables can be written as a bunch of these things, and just notice how these will kind of be like in our standard form. Ax plus by is less than c instead of equals c, or the less than or equal to, greater than, or the greater than or equal to, where a, b, and c are real numbers, which you'll just learn more about at high school level. So as you do want to remember and recall, a solution of a linear inequality is an ordered pair, the x and y, that makes the inequality true. So to be a solution, I need to be able to plug in my x, y, and to have the inequality work to be a true statement. So let's just check how that works. So tell whether the ordered pair is a solution to the inequality. So really all I'm doing is plugging in the numbers for the x and the y. So again, here's the ordered pair x, y. So I first just plug in the x goes in place of the x, the y goes in place of the y, and I have to decide if that's a true statement or not. So following my ordered operations, I get negative 11 is less than negative 3. Is that true? And yes, that is a true statement, so it is a solution. Okay, so for example B. For example B, we're going to plug in our numbers. X is a 2, y is a negative 2, greater than or equal to 8. So we get 2 plus 6, 8 is greater than or equal to 8. Well, we know it's not greater than, but it is equal to, so we would say yes, this one is also a solution. Now we want to talk about how to graph a linear inequality with two variables. So first what we're going to do is graph the boundary. Basically what we're going to do is we're going to figure out what this looks like if it was an equation, and that'll be the boundary. We'll show you some examples as we go. Except instead of just drawing a straight line that's bold, what we're going to do is use a dashed line for the less than or greater than inequalities, and a solid line for the less than or equal to or greater than or equal to inequalities. So then what we're going to do is we're going to test a point. So just test a single point that is not on the boundary line to determine whether it's a solution or not. The easiest one to test more than any other point is 0, 0. If 0, 0 is on the boundary, you obviously can't use it. But if it's not on the boundary, that's the easiest one to test, because when you plug in zeros, it'll make your numbers be quicker. Okay? So then what we do is when the test point is a solution, we shade the half plane that contains that point. When the test point is not a solution, we shade the half that does not contain the point, so the other half. And I'm going to show you some examples, so these sets will hopefully make some sense as we go. So here's my first one. We want to graph y is less than or equal to 2. Okay, so coming down here, we've got a little bit of space there, so I'm just going to rewrite this again. So to make this graph, what I want you to remember, this is one that hopefully we're all good with. This is our horizontal line. Okay, we don't have a slope because it's a 0. M being a 0 times x becomes 0. What I want to first do is graph. And when I'm graphing the boundary, I first want you to think of it as y equals 2. Okay? So a couple of things. If I'm doing y equals 2, it would be right here. Okay? It is a solid line because we are doing a less than or equal to. So because of this or equal to, it's a solid line like we would normally graph y equals 2. So then what I want to do is test a point. So to test a point, I'm going to test 0, 0. Again, I can see that 0, 0 is not on my line. So I'm going to test it. So to test that point, the y goes in as a 0. There is no x to plug in, so I just have to look at that. Is that a true statement? Is 0 less than or equal to 2? Yes, it is. So that means this point right here, 0, 0, is a solution. So what's happened here is this line right here has created these two half planes. The top plane up here is all of this, and the bottom half is all of this. So because our test point is in the bottom half, what we're going to do is shade everything below our boundary line, which was the y equals the 2. This is the graph for y is less than or equal to 2. So one last thing we might want to do here is we might want to write this on the graph. That is the graph with that whole shaded area, including the point that we tested that was a solution. So let's do a different one. Okay, so for this one, we are in standard form. You can leave it in standard form and create your graph. If you want to turn it into y equals mx plus b, you could do that too. But one of the important things I want you to notice here is we are definitely going to have a dashed line for our boundary because there is no or equal to. Okay, so just remember that when we go to graph. So if I would like to do this in standard form, which I think is probably the easiest way, hopefully. So remember, my x-intercept, the y is a 0. The y-intercept, the x is a 0. So if I plug in a 0 for the y, the x would have to be a negative 2. If I plug a 0 in for the x, the y would have to be a 1. So again, if that doesn't make sense, we've done this in the past. You should relook at those lessons back when we did graphing of standard form and using our intercepts. You also could rewrite this into y equals mx plus b if you wanted to. And if I did that, I would get y is greater than 1/2 x plus 1. Whichever way you're most comfortable with. So I'm just going to go with my intercepts. If I do negative 2, 0, and 0, 1, I would get those 2 points. Okay? Now remember, we said we needed a dashed line. So that means instead of drawing on a straight edge with my ruler, I'm going to still use the ruler, but I'm going to go up with a dashed line. So this is like our open circle when we did it on the number lines with the one variable. The dashed line is representing the fact that all of the points on that line don't work. Whereas in the first one, the solid line means all of those points are solutions because of the equals part. Without the equals part, the boundary is still what we draw, as if it was an equal sign. The dashed line means that all those would actually not work. So now when I test my point, again, I'm going to test 0, 0, because it's clearly not on my line. So when I test 0, 0, I would have negative 0 plus 2 times 0, which again, this is why the 0, 0 is a perfect one. Basically, I get 0 is greater than 2. Well, we can hopefully see that is not true. So what that means is I wouldn't leave that point there. So sometimes it's just better not to put it, just kind of know that that's the one you use. What I'm going to actually do is I'm going to shade the other side of my half plane this time, because underneath it doesn't work. So this would now be the graph of negative x plus 2y is greater than 2. So on this next example, we want to talk about creating an inequality first, then graphing it, and then interpreting some solutions. So we have a situation here. We can spend at most $10 on not graphs, grapes. That should be grapes, not graphs, and apples for a fruit salad. At most, what does that mean? So at most means I can spend 10, which is the equal sign, or up to 10. So it's the less than or equal to sign. Grapes cost $2.50 per pound. Apples cost $1 per pound. So first I need to write my equation. So I'm going to refer to the grapes, not the graphs, as my x's, and the apples as my y's. So you could use g's and a's if you wanted to, whatever variables, but think about defining them first. So my grapes are the x. So 2.5x plus 1y is at most $10. So again, I could use standard form because this looks like standard form, or I could turn this into y equals mx plus b, which would then look like, they probably should keep it in y equals mx plus b, so negative 2. Either way, again, because it's already in standard form, and these numbers are cooperative with each other to get nice easy numbers, I'm going to go with the x-intercept and the y-intercept, so remembering that those two pieces. So when the y is a 0, the x comes out as a 4. When the x is a 0, the y comes out as a 10. So then I'm going to come down to my graph. We're only going to focus on the first quadrant. We have our x and our y. The x is representing pounds of grapes, not graphs. Pounds of apples is the y's. So thinking about our numbers, our x-intercept, we have to get to 4, 0. So because of that, I think it's pretty safe that I can just go by half pounds down here. The 10, we probably need to go by ones. And then I just plot my 2 points and I see what I'm looking like. So I have 0, 10 is 1 point. I have 4, 0 is another point. Now, before I connect these two dots, is this going to be a dashed line or a solid line? Well, it's going to be a solid line because of this or equal to piece. So once I determine that, I'm going to use my straight edge, and I'm going to connect the dots. If it said you had to spend less than $10, you would need to put the dashed lines. Now, to test a point, again, I would test 0, 0. So 0, 0 is a clear, definite one to test right down here. So if I plug in the two zeros, I get 0 is less than or equal to 10. That is a definite true statement, which then means my shading includes all of the stuff underneath that. Now notice I didn't do quadrants 2, 3, and 4 because is it possible to even have negative pounds of apples and negative pounds of grapes? No. But we do have one more piece here. So remember, interpret, explain the numbers. So we were asked to take two solutions, any two solutions, because these are all solutions to this situation. And because it's a solid line, anything on the line is fair and anything underneath. So I'm going to pick two solutions. I'm going to pick this one right here, and I'm going to pick this one right here. Okay? So, two solutions. So I'm going to pick 0.5, comma 4, and I'm going to pick 2.5, comma 1. So what do those mean? What those mean are, if I buy 1/2 a pound of grapes, I can buy 4 pounds of apples. I could actually buy more than that because I could go as far up as 9 to make that work. But I could buy that combination. So remember, the X's are my pounds of grapes, the Y's are my pounds of apples. So for the second one, I can buy 2.5 pounds of grapes and 1 pound of apples. So I just want you to notice we picked two solutions that would have been less than $10, right? Paying attention to the question, if it said, what are some combinations that would be exactly $10, those would be all the points that are, in this case, sitting right here. So I would have focused on the 4, 0, for example. If I buy 4 pounds of grapes, I can't buy any apples. Or the 0, 10. If I buy no grapes, I can buy 10 pounds of apples. And then obviously any of these other points along the way I could pick as well. But because we have the less than or equal to, all of these combinations are solutions. So we could pick the ones that we picked as well. So remember, when you're graphing inequalities, you first think like it's an equation to figure out what that boundary line is going to be. It's dashed if it's less than or greater than. It's a solid line if it's less than or equal to or greater than or equal to. Then you test a point off of the boundary. Ideally, 0, 0 is the best one to look for because it makes your calculations simple. If your test point is a solution, you shade that whole half of the coordinate plane. If it's not a solution, that means shade the other half. And that will give you the graph of your inequality in two variables. If you have any kind of questions, please feel free to ask me the next time I see you in class.